Okay, today we're gonna finish off exam one review. Let's get started. Okay, so the first one is asking us to rank the following in order of reactivity towards ethene. So here we're talking about reactivity in terms of Diels-Alder. So in Diels-Alder, you have a diene and a dienophile that we react with each other. So ethene is one of the most basic dienophiles that you're gonna see in the Diels-Alder. And so what you need to know is that the diene is the nucleophile in this reaction, and the dienophile is the electrophile. So we do this, or knowing this is going to help us in determining which one is going to be more reactive, because here we have a whole bunch of dienes that were being shown. The difference between all of them is the substituents that are on them. So they have different electron withdrawing groups and electron donating groups, and we need to know what the diene would prefer to have a better reactivity. So nucleophiles, we know that they like a lot of electron density. So we're going to want something that's donating electron density towards us. So if I'm the nucleophile, I want something donating towards me so I can have more electron density in me. So my diene prefers electron donating groups, whereas my dienophile is the electrophile. It's the positively charged. It's more positively charged. So something that's going to help us be more positively charged is an electron withdrawing group. So let's put that down. Okay. So we're going to be looking for electron withdrawing groups on our dienes. So the first thing that we're going to do is identify all of them. So NO2 is an electron withdrawing group. It's one of the best ones. These methyl groups are electron donating through the inductive effect. Because carbon is we have electronegative things and we have electropositive things. Carbon is something that's electropositive. So in terms of electronegativity, we know that it likes to pull away electrons from whatever we have over there. So we pull electrons when we're electronegative. And if I'm electropositive, I push electrons. So these carbons on the side, those substituents, are going to be pushing electron density into our diene through the inductive effect. These we have lone pairs near our diene. They're going to be donating electrons, electron donating groups through resonance effect. So I'll just give you an example of that. If you draw your resonance structure for this, when we resonate, we are putting a carbanion or a negative charge on a carbon. And so this means that we're donating electron density throughout the diene. So that's what we want. Electron donating group, okay. Now we identify this group over here. This is going to be electron withdrawing through resonance as well, because you can resonate like this. And you'll have a carbocation once you draw the resonance structure. And this is a trans, or locked in trans diene. In Diels-Alder, we always have to have an S-cis conformation for our diene. So when we're locked in trans, there's no way we can get out of that to go back to S-cis. So this is going to be our least reactive, because it won't undergo Diels-Alder at all. Okay. For the least reactive, okay, that's the least reactive, and the most reactive is going to be something with an electron donating group, and it's probably going to be the only electron donating groups we have are these two, and I'm going to say that this one is our strongest one because it's an electron donating group through the resonance effect. Then for 4, I'm going to number this one because it's still an electron donating group, but it's just a little weaker than the resonance effect because it's going through inductive. Then our last ones. Okay, so We have electron withdrawing groups on our two last ones, but we want the weakest electron withdrawing group because I'm a diene and I want something to donate electrons to me, but if there's nothing that donates electrons to me, I want the weakest electron withdrawing group that I can have. So between these two, the NO2 and this group right here, this is going to be my weaker one, so it's going to react a little faster. This is going to be 2. So for this, I think you're going to have to know the ranking system of your electron withdrawing groups, like which electron withdrawing group is the strongest and which is the weakest. So there is a ranking series on your book, so you should definitely check that out before your test. Okay, let's go to the next one. Rank the following in order of reactivity towards 1,3-butadiene. This is 1,3-butadiene. Okay, 1 being the least, 3 being the most. Okay, so again, we're asking basically we're looking at the dienophiles right now. We know that they're electrophiles and that they like electron withdrawing groups. So this is what we're looking for, electron withdrawing groups. Then I look at each one of these. And first thing I have to do is identify electron withdrawing or donating. This is going to be electron donating because we have a lone pair right next to our double bond, which is going to donate electron density on my dienophile. So let me draw the resonance structure so it shows how we're donating. Oops. Okay, there. When I drew my resonance structure, I put a negatively charged carbon ion in place of where the double bond used to be, meaning that I'm donating electron density towards that double bond. So then we have an electron donating group on this one. And change my color. Here we can resonate outwards. My resonance structure is going to put a carbocation on the carbon where the double bond used to be. Let me draw the resonance structure so it shows that. So electron withdrawing group. This last one, it's still dienophile, but it looks a little weird. It's just a carbon chain. So again, any carbon is electropositive, and it's going to be pushing electron density into my double bonds. So then we're electron donating group through the inductive effect. Okay. So now let's order. We want electron withdrawing groups in our dienophiles, and the only electron withdrawing group right here is this one. So I'm going to number this as number 1. Change my color. Okay, now we have 2 electron donating groups, and we said we didn't want electron donating groups, but since we have to choose which one is more reactive than each other, we're going to choose the weakest electron donating group. So then my weakest electron donating group is going to be this one right here. And I'm going to put this as number 2 because it's donating electron density through the inductive effect, whereas the other one is through resonance, a more powerful electron donating group. And then we are going to number the last one, number 3. Oh, I numbered it the wrong way. Oops. It's the same thing, I just switched my numbers. So this one is going to be the least reactive. So 1, 2 still in the intermediate, and this one was their most, because we prefer the electron withdrawing groups. We're good with that one. The next one is rank the following in order of decreasing pKa's. Okay, so for this one, I just wanted to list out some of the pKa's that you should know. So for the acetic acid or the carboxylic group, It's going to be a pKa of 4.8. Okay. Now I'm going to look at something a little similar to it. So this is acetic acid, and right over here we have benzoic acid. So the benzene ring on my carboxylic acid group is going to be pulling electron density away. Let me draw my... Actually, I don't need to draw this. I just want to show why this one is going to have a lower pK. The pK of this one is going to be 4.2. And the reason because of this is we know that the stability of the conjugate base determines acidity. So increasing acidity equals stable conjugate base. So I'm drawing my conjugate base over here. And so this conjugate base, something that's also like withdrawing electron density from this group right here is going to be the benzene ring, whereas this one over here only has the carbonyl group, the C11O. So this one is going to be more stable base, meaning it's going to be more acidic. Something that's more acidic is going to have a lower pKa. So that's why this one is pKa of 4.2, whereas this one is a pKa of 4.8. And we're going to make that relation one more time. I'm going to go to ammonium. The pKa of ammonium is 9.4. And then I'll go to phenol. That's one of the ones that we should know. So phenol's pKa is 10. And then I included this one right here. This is not one of the pKas that we should remember. So in OChem 1, you were given a couple of pKas that you should memorize. And in OChem 2, they're adding a few more, I think about like 4 more. And so those are really the pKas that you should memorize so that you can tell the pKas of any other compound. Because there's like millions of compounds and you don't want to memorize millions of pKas. So you memorize the ones that we're giving you so that you can approximate the other ones. So that's what we're going to do with this one. This is called, I'm going to give you the nomenclature for this because you're going to have nomenclature on your test. This is p-chlorophenol. Phenol is the common name of this one right here. So we have a phenol group right here, and para to the electron donating group is our chloro group. So p-chlorophenol. I'm trying to decide if the pK is going to be smaller or it's going to be greater than or less than 10. So here's what we're going to do. We're going to draw the conjugate base. So let me draw the conjugate base of this one. Okay, so the difference between these two is the one on the right has a chloride group. So the chloride group is a halogen. We know that halogens are electronegative and they like to withdraw electron density. So this withdrawing group is going to stabilize our base because what it does is it delocalizes electrons. And something you should know about OChem 1 is the delocalization of electrons on a compound provides stability. So this chlorine is going to delocalize electrons and make this the more stable, stable compound. So this conjugate base is more stable, meaning it's more acidic. So then our pKa should be less than 10. We don't know the exact pKa because that's not something that we need to memorize, but we can know like the approximation. And I think we're good for this one. Yeah, we have the pKas for all of them, so we're good for this one. Next one I'm going to do is, which of the following is a stronger acid and why? So again, we're following the same rule, higher acidity, more stable conjugate base. So I'm going to draw the conjugate base for each of them, which is just plucking off the hydrogens that they're showing us. There we go. So something that you should immediately notice is the conjugation. So conjugation is 3 consecutive sp2 atoms, right? So I'm going to highlight all my sp2 carbons. On both my compounds. So both of them are completely conjugated. They're all the carbons are sp2, and then I'm going to note on the side because it looks weird. Like, why are we saying that a carbanion is sp2? You should remember sp2. A couple of things that you're going to see that are sp2 are carbocations, carbanions, and radicals. So those count as sp2 as well. So then completely conjugated, but the one on the right is a cyclic compound. So since it's cyclic and completely conjugated, we know we're probably going to be looking into the aromaticity of this. So we check off some of the boxes. So some of the boxes down here, these are the rules for aromaticity. This is completely conjugated, complete conjugation. Okay, so then since we're completely conjugated, we're planar. That's one of the rules. If we're completely conjugated, that means we are planar. We are cyclic. This is a cyclic compound. And now we need to see if this follows Heckel's law. Number of pi electrons. So I'm going to count my electrons. 1, 2, 3, 4, 5, 6. 6 pi electrons. We don't count these right here because they're out of the ring. Anything outside of your ring, you don't count. And you get that n is going to be a whole number. N is 1. So whenever you get a whole number for Heckel's law, that means it obeys Heckel's law. So any whole numbers can be like 0. So that's one of the important ones. 0, 1, 2, 3 onwards. No decimal points, no fractions, right? So this obeys Heckel's, meaning that this conjugate base is going to be aromatic, meaning it's really, really stable. Okay. The one on the right is not cyclic, so that's already out. We're not aromatic here, but we do show complete conjugation. Complete conjugation, which also makes it stable, but you should know that something that is going to be aromatic is like stability on steroids, is what they like to say. So then this is going to be my more stable conjugate base, meaning that this one should be more acidic. Acidic. There you go. So that's going to be a stronger acid. It's going to have the lower pK. Then I'm going to move on to down here. Label the following as aromatic, anti-aromatic, non-aromatic. Assume all fully conjugated cyclic compounds are planar. Okay, so I was given this question on the test, and this part just confused me because it didn't allow me to recognize whether if I was like non-aromatic or anti-aromatic. So I just completely crossed that out. And so I drew all of my checkboxes here so that I can tell what's aromatic or not. And so I left off some notes on the side. So if all my boxes are checked, meaning we have Heckel's law obeyed, cyclic, planar, conjugate, complete conjugation, you're aromatic. If the only box that's not checked is Heckel's law, we're anti-aromatic. And if there's more than one not checked off, like if Heckel's law is not checked off and some of them are like not cyclic or not planar, that means you're non-aromatic. Okay, so let's check this out. I'm going to say this is A, B, and C. For A, we have a bicyclic compound, and so anything within those two cyclic, within this compound, these two circles, we're going to count for pi electrons. Okay. So 2 electrons in each double bond, each pi bond. 6, 7, 8, 9, 10, 11, 12, 13, 14. And do Heckel's law. 4n plus 2, 12 equals 4n, and equals 3. N is a whole number. N is a whole number. So we obey Huckel's law. So that one's good. We are a cyclic compound. We're completely conjugated. All my carbons in this bicyclic compound are sp2. And so since we're completely conjugated, we're planar. So this is going to be aromatic. Okay. Okay, so I changed my color so I can like not get confused on this. This one is going to be a little bit more challenging because we need to know what counts as pi electrons. So just know that if your electrons on a heteroatom are in the p orbital, you're able to resonate, and then you can count those as pi electrons. So these lone pairs, okay, another like hint at this is that if your heteroatom has a double bond on it, like how this heteroatom has a double bond on it, there's already something taking over the p orbital. So the electrons on this heteroatom are in the sp2 orbital. They're not in the p orbital. And you wouldn't count these electrons in your pi electron count for Huckel's law. But oxygen, a heteroatom, is not double bonded to anything. So these lone pairs are able to resonate and they're in the p orbital. So we're going to count these for Huckel's law. So I'm going to start with those. 1, 2, 3, 4, 5, 6. We'll do Huckel's law real quick. And n is equal to 1. N is a whole number. Huckel's law is checked off. We are completely conjugated. Even our heteroatoms are conjugated, so I'm going to check that off. Since we are completely conjugated, we're planar, and we are a cyclic compound, so this is going to be aromatic as well. Okay. For the next one, anything outside of the ring, that's the key for this one. Anything outside of the ring, we're not counting as pi electrons. So let me count my pi electrons. 1, 2, 3, 4. Do Huckel's law for this. Oops, plus 2 equals 4. N is equal to 1/2, a fraction, which is not a whole number, so we don't obey Huckel's law, and I'm not going to check that off. We are a cyclic compound. We are completely conjugated, so even though it's outside of the ring, like I feel like that would confuse someone, we're still sp2. We still have 3 groups around that carbon. We're still sp2. So we are completely conjugated. All of these are conjugated, meaning we are planar. Okay, so then you look back at your notes. If only the Huckel's law is not checked off, then we're anti-aromatic. So I'm going to label this as anti-aromatic. There we go. Well, let me do this next one. Draw frost circles of the following. Determine if the species is aromatic or anti-aromatic and explain why. The frost circles were intimidating for me at first, but then one of my star series taught me a little trick. So, or not a little trick. I feel like everyone teaches this, but it was so easy when she explained it. So I'm going to count the carbons in my cyclic compound. 1, 2, 3, 4, 5. I'm going to draw 5 dots. And I'm going to make sure that one of my dots hits the bottom of the circle. Then I'm going to connect my dots. And draw a line on every vertex. I think they're called vertices. There we go. And we're going to label all of them. So this is going to be psi 1, psi 2, psi 3, psi 4, and psi 5. Then I'm going to draw my non-bonding line, which is just cutting my shape in half. Non-bonding. And I should know that anything on top of the non-bonding line is anti-bonding. And anything below the non-bonding line is bonding. So then I'm going to count my pi electrons on this compound that we're looking at. And I see, so we have a carbon ion here, so we should know that we have a pair of electrons on my carbon. So I'm going to count these two. 1, 2. Then the double bonds, 3, 4, 5, 6. Okay. So then each of these 6 equals the pi electrons. So we're going to fill each of these energy levels with our pi electrons. So I'm going to do, let me change my color real quick. Oh, I forgot to do this right here. These little asterisks are assigned for like anti-bonding, and those are something that you just have to write for sure. Then I'm going to change the color, fill in the energy levels. 1, 2. That's 2 of my pi electrons. 3, 4, 5, 6. Okay. So my bonding orbitals are completely filled, and that is why here we are aromatic. Bonding molecular orbitals completely filled. I'm going to say aromatic because bonding orbitals, molecular orbitals are completely filled. That's why we're aromatic. And we can just check that we're right on this, because this question is asking us about molecular orbitals. So then our explanation should be using molecular orbitals. You can check if you're right using the Huckel's law or whatever, but you're not going to include that in your explanation because that's not what they're asking you. This is just for you to check yourself. So I'm going to do my Huckel's law. 4n plus 2 is equal to my 6 pi electrons that we counted, and n is equal to 1, a whole number. So we know that we're aromatic. And this is just for us to check ourselves, but this is what we should be using to explain a question like this. Okay. Then I'm going to do another circle. This one's going to be a little harder though, because I think these are 7 edges. 1, 2, 3, 4, 5, 6, 7. Okay. Draw my circle. Make sure that one of the dots hits the bottom. So 1, 2, 3, 4, 5, 6, 7. Yeah, that should be good. Connect my dots. Put it in the middle. Write a line on every vertex. There we go. Know that the line, the imaginary line, is a non-bonding line. Anything below is bonding. Anything above is the anti-bonding. So then I'm going to label myself. This is side 1, side 2, side 3, side 4, side 5, side 6, and side 7. Anything above the imaginary non-bonding line is anti-bonding. So then for each of your sides, you should put an asterisk on them to label them as anti-bonding or non-bonding. Or yeah, anti-bonding, sorry. So then I'm going to count all of my electrons, my pi electrons on that compound that we were looking at, starting with the ones in the double bonds. So 1, 2, 3, 4, 5, 6. Okay, cool. Then I'm going to add them onto my orbitals. 1, 2, 3, 4, 5, 6. Okay. Looks like we're going to be aromatic again, because our bonding molecular orbitals are completely filled. Okay. I should have chosen like a smarter way to do this, like one aromatic and one non-aromatic, but I apparently messed up. So these are good, but I wanted to show you something that was going to be anti-aromatic because that might be on the test as well. So just know that if your bonding molecular orbitals aren't completely filled, like look at this. Let me erase this one. If you had only Yeah, if it was only partially filled, you'd be anti-aromatic because your bonding orbitals are not completely filled. But here we are completely filled, so we're good. If some of your anti-bonding molecular orbitals are filled, even if they're completely filled, you're going to say anti-aromatic because my anti-bonding orbitals are being filled. There we go. Let's move on to the next couple of reactions. So write the product for the following reactions. Here, this is one of the newer ones that we have been looking at. So I'm just going to list out like what is my Lewis acid and what is my Lewis base, just because I feel like this is something important that you might see in one of your mechanisms. So this is going to be my Lewis acid. This is my Lewis base. This is chlorine is able to donate a lone pair to my Lewis acid. My Lewis acid doesn't have lone pairs at all, and so in the mechanism when you're donating lone pairs, you're gonna make a little complex that looks like this. You'll have a negative charge on your aluminum and a positive charge on your chlorine. So that's the complex that it makes. And I'm not going to show you the whole mechanism for it. I'm just going to show you the complex that it makes. And it's important to know what is your Lewis acid and what is your Lewis base. But the important thing for this one is identifying your electron withdrawing groups and your electron donating groups. So this ether on this side is going to be electron donating group because it has a pair of lone pairs right off of the benzene ring that it can donate into the benzene ring. So it's donating electrons. Whereas this NO2 group, this nitro group, is going to be an electron withdrawing group. It's one of your stronger electron withdrawing groups. So what you should know as well, when you're doing Friedel-Crafts acylation, you are going to direct the substituent using the activator. So you have an electron withdrawing group and an electron donating group. Your activator is the electron donating group. So wherever the electron donating group is telling you to go, you're going to put it there. So electron donating groups, we know that it likes to direct to ortho and para. So ortho to the electron withdrawing group are right here, and para is right here. The para position is being taken over, so we're only going to write one product. Draw everything the same. And we're only going to write one product. Or substituent coming off the benzene. And that's what it will look like. So just notice that we're basically cutting the chlorine off and attaching it to a benzene ring. This is like the easiest way to look at it. Then the next one, we have a Diels-Alder. It's a closed ring, so we know that we're gonna have that weird bridged compound. So here, it's not asking for the mechanism, but I think it's really helpful to do the mechanism for Diels-Alder, just so that you don't misplace any of the substituents or don't drop any carbons or things like that. So I like to number only the carbons that are going to be reacting in this Diels-Alder, which is the ones that have the double bonds. And we know that we're going to be breaking a double bond to connect to carbon 6, breaking this double bond to connect to carbon 4. Carbon 4 can't have 5 bonds because carbon only likes 4 bonds. So we're going to resonate this over between 2 and 3. So we again know that since this is closed, we're going to make that weird bridge form that looks like this. Name this carbon 1, 2, 3, 4, 5, and 6. We know that we have a double bond between 2 and 3 because that's what we resonated. And we are missing this part. We skipped it because we only told us like what's reacting. So here I'm going to draw a bridge because that's what we were skipping. Because between carbon 1 and 4, you have a nitrogen attached. So again, between carbon 1 and 4, nitrogen is still attached. And you have your little bridge system right there. Then on carbon 5, we still have substituent, and we're going to put it in the endo position. COOH. You don't need to draw it out, just use abbreviations. And I put it only in the endo position because the endo position is the most stable position on this bridge. Just because, I mean, on this compound, because the nitrogen group is going upwards, so it's a bridge. And if I put my carboxylic acid group going upwards as well, there would be steric interactions between them. So since I'm putting my carboxylic acid going downwards, we have less steric interactions and we have a more stable compound. So that's the only product that I'm going to draw here. Then let's move to the next one. NBS. This is kind of an annoying reaction because here we have lots of products, like lots of products, because we're able to resonate. And I'm sure she's not gonna, or they're not gonna put any compounds that are too difficult because there's a lot of resonance having to do with this. A tip that you should know is, okay, so NBS adds bromine to the allylic carbon. NBS is also a radical. Let me write that down. So radical reaction, and then provides bromine. Provides bromine to allylic carbon. Okay, so I'm going to, just looking at this compound, put all my radicals in the allylic position. And then I'm going to bring one of them down. So this radical, this is already somewhere I can place my bromine. Or I'm just going to place my bromine on all the places that I place my radicals in this one right here. So bromine, that's one. Bromine, that's another one. And bromine. So those covered the radicals that we were talking about. But I'm going to bring each of those radicals down. And I'm going to write a resonance structure for each of them. So again, we're talking about radicals. So only we're going to have half arrows. Break this double bond and make another double bond in another place. My resonance structure should now look like this. So that's another place I can place my bromine. Okay. Again, looking at this radical that we drew, I'm going to break the double bond, place the electron somewhere else, put the radical on the same place, and draw my resonance structure. And I'm going to put the bromine there as well. See, it's a little tedious, but I'm sure they're not going to put this, something like this, like something with a lot of products. But I just put this here because this is something that you should know, the little tricks for these. And they're probably going to want you to resonate as well. So draw my resonance structure. Okay, that's my new resonance structure. I'll put the bromine in place of the radical. So these should be all our products for this reaction so far. Circle them. Ah, there we go. Next one. This is another kind of, it's similar to Friedel-Crafts. What you should know about HNO3 and H2SO4 is it's just adding an NO2 group, nitro group. So let me make sure we're good so far. Yeah. Okay, so identify your substituents in your benzene ring. We have 2 electron donating groups, again, through the inductive effect. But electron donating groups are still going to put the substituents in the same place. Electron donating groups always put them in the ortho and para position. Ortho para. So ortho and para to this methyl group right here. So this is ortho and this is para. I'm going to do the other one in a highlighted one so we don't go over anything. So ortho to these are right here and para is right here. So it looks like we're going to be drawing, okay, this is one of the trickier ones. Okay. What you should know about this one is that if you were to place the substituent right here, there'd be a lot of sterics between these methyl groups and the NO2 group that you just added. There'd be 3 consecutive substituents, and that's not something you want. You don't want to add between anything. So we're not going to put the substituent there. We can put it on the other ones though. See, that's one that we can put. And the other one, if you want to draw it, you can. They're not going to mark it wrong, but I'm pretty sure, let me just draw it out to see if I'm correct. These are going to be the same structure. Yeah. These are the same structure, basically just like flipped or, yeah, just rearranged. So you can draw both of them because she's not going to mark them wrong because you're drawing the right answer, but there should only be one. That should be your answer. This next one is one of the ones that I made sure to really look into before my exam. So in the Friedel crafts, well, excuse me, in Friedel crafts, there's a couple of exceptions. So when, oh yeah, this is gonna be my Lewis acid, and we look for our Lewis base now. And we usually say this is our Lewis base, but we have a nitrogen group right here. And we know that nitrogen is usually a really good base. So instead of chlorine being your Lewis base, your nitrogen is going to be your Lewis base. And so we're not going to be able to proceed with the Friedel-Crafts reaction because of this nitrogen group right here. It's making a different complex, and this one's not going to want to break at all. So I'm going to say no reaction. And if they ask you why, which on my test they asked why, and I didn't really read right for this, so that was my bad. But if they ask you why, you should draw this right here and write that this is your Lewis acid and this is your Lewis base, and that'll be enough explanation as to why there's no reaction on this one. The next one, HBr. So we're doing addition here, and we usually have 1,2 addition or 1,4 addition. Here we're going to do 1,4 addition. Because of this 90 degrees Celsius. So when you have high heat on an HBr reaction, that means you're going to want your thermodynamic product. So thermo product. And this usually is talking about the 1,4 addition product. So I'm going to number going this way. 1, 2, 3, 4. The reason I'm numbering it like that is because before you do your 1,4 addition product, you have to do 1, 2. So there's a whole mechanism for this. So let me show you the mechanism for right now. So we're following Markovnikov's, and we usually want to put the hydrogen in the place that is going to give us our most stable carbocation. So that'll be on this carbon right here. Oops. So adding this hydrogen on this carbon is going to give us a tri-substituted carbocation, which is something, it's one of the most stable carbocations. So that was our first step. And if we were to attack with our Br group that we just broke off over here, they would give us a 1,2 product, which we don't really want because, again, we added the hydrogen here and we would add the bromine here if we wanted the 1,2 addition product. Right now we want the 1,4 because of that heat. It's allowing us to make a more stable compound. So then what I'm going to do is I'm going to resonate this double bond right here So we still have our hydrogen. We resonate this to a different place. And we have a carbocation on a terminal end, which we usually don't want, but this is stabilized by resonance, so this is okay for now. And now we can add the bromine. We can let it attack to make this product right here. And that'll be our 1, 2, 3, 4. Our 1, 4 addition product. So remember, when you have heat, you want the thermal product. You want the 1, 4 addition. When you have like negative 70 degrees Celsius, you want the kinetic problem. And you want the 1, 2 addition product, which would have stopped on this one. This bromine would have attacked and we would have the 1, 2 product. And now I'll just draw out that, I'll draw out the 1, 2 product. This is a side note. Okay, cool. Pretty sure we're done with this worksheet. If you have any questions on the worksheet, make sure to contact me during office hours or email me or whatever is best for you. And good luck on your test. This is the end of part 3. Good luck, guys.